first, let's talk about the idea of a sample. So to understand the idea of a sample, we need to understand that in any problem we are trying to solve in terms of statistics or probabilities, we are really thinking about a large population, whether this population is of measurements, whether this population is of actual individuals. And this is where our problem starts. It starts with a population. Let's imagine that we have a full population of yellow balls in this example, and every ball is numbered either from 1 to 9. So our population, let's say we captured all this type of circles or balls in our population, and they are presented here. And each of them has a value. Let's say it's the ball's age, or it's the ball's weight, whatever you want to think about it. But let's say we have all these yellow balls in the world captured over here, and they have numbers from 1 to 9. Now when we have this population, we cannot really make our study on the full population, because the population could be billions if we're talking about human beings. The population could be thousands if we're talking about some fish in a lake. So we can only work with a sample. So how is this sample created? We're taking random selections from our population. We're trying to make it as random as possible and building up a sample. The sample will never be as big as the population. Ideally it should, but we can never reach to that. But it should be randomly sampled to reach a situation where it is representative of the larger population. So this is what we are trying to do. We're trying to build a sample that is representative of the population, and hence make some calculations on it to build some inference. So in reality, we can only work with a sample. We can never have the full population. But the question comes, as this little smart kid is thinking, what can we tell or what can we inference about the population from this sample? So let's say we have a sample that is representing 10% of the population. What can we tell about the population fully from this specific sample? So can we, for example, know the mean of the population? So for example, if we have the heights of children at the age of 10 all over the world, can we take 100 or 1,000 or 10,000 kids at the age of 10 and measure their heights and be able to tell what is the large population's mean of height? What is the variance? How do they differ from the mean? And more importantly, what are the probabilities of, for example, children being as high as such or as short as such given that sample? And what is the mode? What is the value that we see repeating the most? So things like this are the things we are trying to infer from a sample on the full population. So this is the first part. We need to really distinguish between a population, which includes all observations or all individuals available, and a sample which represents a percentage of that population that is supposedly randomly selected to a point where it is representative of the distribution of the population. We said distribution, so what is a statistical distribution? Now let's say we have this jar of the sampled balls that we got from the population of probably, I think they were 100 or something. And let's say we start checking what values are existing in our sample, and we start stacking them. So we will take one ball from this jar and put it on its location. So we have 1 1, we have 2 1s, we have 3 1s, until we get all the 1s and stack them over each other. We will do the same for the 2s. We will do the same for the 3s, same for the 4s, same for the 5s, and so on. We will end up with a distribution or with a graph that shows us how many 1s do we have in our sample, how many 2s do we have in our sample. So we can just count them. So by having the frequency of the representation of every measurement in our sample, we can build some type of a histogram or some type of a frequency count for the measurements that we got from our sample. Now if we go one further step and normalize this measurement, so instead of saying 7, we want to say that we have a total of 33 balls in our sample, and 7 over 33 of them are ones. 6 out of 33 of them are twos. 6 out of 33 of them are threes, and so on. So by this we will have a percentage that we can expect the big population to have of ones. Because remember, we randomly selected the balls and we ended up with the majority being ones. So we can kind of tell that the majority of the population could be ones. So this is what we have now is a probability. Because think about it. Now what is if I'm taking a ball from the full population, the probability of this ball being 5, for example, as you see here, is very low. Because when we took 33 balls from the large population, only one of them was a 5. So the probability is around 1 over 33. Whereas if I take a ball, it might very well be a 1, because 1 was the most represented in terms of proportions within our sample, and so on. So I can tell, for example, the probability of picking a 2 is around 6 over 33. The probability of picking a 2 or a 3 is almost equal, because when I sampled 33 from the large population, I ended up with the same number of 2s as 3s, and so on. So this can give us something about the probability statement. And this is a statistical distribution. So we basically distributed over the numbers we got from our sample, and we counted how many times did we get each number. Of course, these can be numbers, these can be colors, these can be a certain category of individuals, but basically we are checking how many did we get in our sample from every category of interest, and then normalizing by dividing it by the total, and having percentages that state what proportion of each category is represented in our sample. And this, in a nutshell, is probability in a frequentist paradigm. So in probability, we talk about frequentist or Bayesian. So in frequentist, it's about the frequency. It's about what are the chances of getting this number. For example, if I roll a dice, the dice has 1 to 6. So if I roll it, for example, 10,000 times, I expect to have the same number of ones as the same number of twos, or a comparable number with all the numbers. So it's a fair dice that has 1 over 6 probability for every number. Whereas a population of random balls that could have different measurements could have different proportions. So probability really is telling me the proportion of seeing a certain measurement within my population. Let's think about it a little more in an example. So if we have a sample of adult males and we are interested in the adult male weight distributions. So if we think about it, adult males probably around the world are something around 3 billion, because they're supposedly 50% of the full human population. So if we have a sample of those adult males, let's say 10, let's say 20, let's say 100, we will just start stacking them over their actual weight and seeing what values we are seeing the most. So we are seeing a condensation around 75 or 76, and we are seeing values that are going over the right and over the left of that. So basically this is how we start building a statistical distribution of our sample. So just like the example before, we stacked the values that are similar to each other above each other. So we ended up with a distribution that is showing the sample we have, let's say, stacked over its measurements. So we have, for example, one who is below 50 and one who is as heavy as 125, whereas most of our sample is falling around 76 or 77 or somewhere in that range. So this can tell us that the expected value of picking a random adult from our population or our world at large would be somewhere around 76. It's inferred from the mean of the sample that we had. And we can also have a range or an idea of how wide our measurements could be by checking the variance. So we can see, for example, in this sample that some went as low as around 48 and some went as high as 125. So we can tell about the center of the distribution, we can tell about the range or the width of the distribution, and all these are type of interesting measurements. In fact, when we look into the distribution we got more, we see that it looks like a bell curve. And this bell curve is what we call, or what you probably heard of as the normal distribution. So there's a theory, it's called the center limit theory. We're not going to discuss it here, but basically the more samples you get, the more probability that from a natural phenomenon, the more chances that they will look like a bell curve. They will be centered around a certain mean and deviating from that mean towards the left or towards the right with a given variance. So this is one of the very famous statistical distributions or common distribution, which is called the normal distribution. Now, why are they useful? Why didn't we just have our sample and end there? Well, statistical distributions are useful because they give us more confidence in any inference we make about the values that are outside of the sample. So remember, now if we wanted just to say, for example, how many adult males that I have that are of a weight of 76 kilograms, I cannot just count the ones I have in my sample, because really my sample is just a sample. It's not of my interest. My interest is to make an inference about the bigger population. So once I have a distributional form that is inferred from my sample, I can apply this distributional form on the population at large and have more confidence in making any inference about the mean, about the variance, about the predictions I will be making in my population. So they enable us also calculating point estimates. So for example, when we saw this distribution, we could have said that the actual mean as a point estimate is around 76 or 77 for the mean and the variance, for example, upon knowing the distribution parameters. But when we talk about distributions or statistical distributions that we will see in the next episode, we can tell a lot just by knowing the parameters. So for example, for the normal distribution, we only need to know the mean and the variance, and we can infer everything else. For the Poisson distribution, we can know just the rate, tell so much about the expected value, about the variance, and about the mode, and about so many different things. So basically, distributions make great statistical summaries of real-life situations. Let's say you are interested in modeling the time you wait for a bus on a bus stop. So if you are just taking a couple of samples, one is 7 minutes, for example, and one is 13 minutes, you can say that the average is 13 plus 7 over 2, which is around 10 minutes. But this is a very weak inference, because we know that waiting for a bus in a bus stop is probably following an exponential distribution. And once it's following an exponential distribution, we can infer more about the mean than just taking the average of the sample. So things like this make statistical distributions very useful, and the common distributions that are used to model real-life events much more meaningful than just taking point estimates or statistical summaries that we are used to taking. Now this leads us to something a little more deep into the topic, which is the probability density and probability mass function. Now we talked about the balls example, and we said that the probability in a frequentist paradigm is that I will select a 1 with a chance of 7 over 33. I will select a 2 with a chance of 6 over 33, and so on. So basically, the probability function tells us something about the probability of getting a certain measurement or a certain value from our data at large. Let's look at this example. This is a discrete random variable that is either 1 or 2 or 3. It cannot be 1.5 or 1.2. So we basically took that sample of the discrete random variable that we have, we stack them above each other, and as we see here, for example, we have low number of 1s, we have higher number of 2s, we have higher number of 3s, and so on, while most of our values are falling between the 3 and the 4 and going down from there. So this is a discrete distribution of a random variable in the form of a probability mass function. Why is it called a mass function? Because the mass of the ones are stacked above each other in that place. the mass of 2's is stacked above each other in the second place. So it's basically like a histogram. So this is the probability mass function. It works with discrete data. And if you remember, we normalized it because we're interested in proportions. So what is the proportion of ones? So we divide by the full count. So it was, for example, 7/33 in the first example. So none of those bars can be bigger than 1 because we divided by the total. So it's going to probably be in a range of 10%, 20%, 30%. The highest we can ever get is 100% if all our data is of a certain measurement. So the P of x, the small p of x here, is the probability mass function, and it ranges in the values between 0 and 1. If you think about it also, it sums to 1, right? Because when you divide the whole thing by the total and you normalize it, and then you have 7/33, then 6/33, then 6/33. If you sum all of these, eventually they will be 33/33 and they will be 1. And the same thing in any probability mass function. And that's in fact one of the properties of a proper probability mass function, is that it should sum into 1. And the probability in a frequentist paradigm of getting any value of x that is equal to small x. So let's say, what is the probability of getting small x over here equals 2? It will be the length of this bar, because this bar is representing the proportion of the sample that is a measure of 2 in our population. So the probability of getting any specific value is just the value of the length of this bar. So basically the small p of x tells us the probability of getting a certain x value that is equal to the small x. Now if we talk about the continuous data, it's a little bit different, because with continuous data we don't have masses that are distributed. Remember, we don't have actual values, we have different measurements from different values that are probably infinite, because the real numbers are infinite. You can have 1.1, 1.11, 1.111, and each of these is different. So really you have a way of looking at the density. Where is our population more dense, or where is our sample more dense in the measurements? So we have a high density around this number, we have low densities here, but it is never 0, for example, for this curve. So we always have a value that is of somehow of a proportion, but it's not a specific value, it's a density of the sample we have. So the probability density function is different from the probability mass function because it looks at continuous data or continuous random variable. It integrates to 1, it doesn't sum to 1, because you cannot really sum a continuous function. But if you take the integral of it, you will find that the area under this curve for any proper probability density function is 1. So it integrates to 1. But now think about a crazy fact. What is the probability of getting a measurement that is 100.123? It's very, very, very low, because if you think about it, I can have any number in the real number line that is represented. So looking at a specific number of a certain measurement, we can never actually draw this. So if you have a big, let's say, it's difficult to talk about it in terms of the balls, but let's say we have 1 million balls. It's representing a differing point at the 10 to the minus 6. So let's say we have 0.00001, 0.00002, 0.0003, up to 0.9935123, whatever. Having a specific value that I'm looking for is almost impossible. So if you think about it, the probability of getting this number, it's 1 over infinity, because in a frequentist point of view, it's the value I'm interested in over the full range of values. So I'm interested in a single value out of infinite number of values. So it's going to be 1 over infinity, that is 0. If I look at a different number also, which is the probability of getting 100.534, it's also 1 value out of an infinite number of values, so it's also 0. If I want to take for a third example, I want to pull this number out, it's also going to be 1 over infinity, which is 0. So this is an interesting fact about the probability density function that is different from the probability mass function. So I cannot just say probability of x equals 3, for example, is this number. So what can I do? Look at this confused man now. He doesn't know what to do. But this leads us to talking about a cumulative distribution function. So cumulative distribution function allows us to make some inference about certain values' existence within our population. Let's think about this. If I cannot get the exact number, because I can be talking about 3.645 or 3.643, which is a specific number, what if I take a number a little bit above it and a number a little bit below it and just talk about that specific slice of my distribution and say what is the density represented in that, or what is the probability of getting a number in this specific range. So instead of saying, for example, I want to get 3.54231 whatever, I want to see what is the probability of drawing a number between 3.4 and 3.5. So here I'm just saying that my small x is between my small x minus a very small number, which is this Greek letter delta, which is used to represent very, very small numbers, and plus a very small number that is almost a 0 above and a 0 below, but it's really not 0, so it's a little bit above and a little bit below. So I'm talking about a slice. I'm giving it a width instead of the width of 0. Can this be a good approximate to probability of x equal x? Yeah, it's an interesting idea. So if I'm talking about the density of this slice, can I represent the probability of this number by this slice? And in fact, it's a good approximation. So really, what is this? It's basically the probability of x is smaller than x plus delta minus the probability of x is smaller than or equal x minus delta. Think about it. If I want to get the width of that slice in a continuous distribution, I want to take anything that is below the larger value and subtract anything that is below the smaller value, and I will be ending with the difference between these two values, which is that slice that shows me that width of the data being in that specific location. So draw it and convince yourself with it. If you're talking basically about 2 points on a continuous scale, and you're taking the difference between those 2 points to understand what is the width of that region. So now we talked about the whole area from 0 or even from the negative side, if my data was distributed even on the negative scale, until a specific x. So what is this really? This is my cumulative distribution function. So basically it's the sum of all the distribution up until this point. So let's look into it a little more. So if this is my probability density function represented by small f of x, and it looks like this, if I want to talk about the probability that x, the large X, is smaller than this specific small x, the yellow, I'm talking about this region, because this region is somehow representing the probability of x being small than x. So any point over here is of the larger than x. Any point over here is x is smaller than the small x. The same thing if I'm talking about this point. If I'm talking about this point, any point that has x value less than this yellow x is falling in this range, whereas any point that is having x bigger than the small x is falling in that range. And the same thing for here. Now let's think about it a little more. You see this, now the red region is the full area under that distribution curve. And the yellow region is just my area of interest. So as we said, from a frequentist point of view, we're interested in the proportion. So we're really saying that the proportion of my data that is below a certain number, which is the CDF, is the division. It's the ratio of this yellow region, the small region, over the red region. Because remember, these curves are created by stacking all the values I have. So here I have more values of that specific number. Here I have less values of the specific value of x. So if I'm interested in the chance of drawing a value that is in the yellow region, its proportion is the yellow over the full, right? Because I'm interested in getting a certain value that is represented with this proportion, which is the yellow over the full region, and this is the chance of drawing it. Now, what is the red region? If you remember from a couple of slides before, we said we normalized. So everything here is integrating to 1. So really the region under the full curve, which is the red region, is 1 because it's normalized. It's a proper probability distribution. So really the probability of x is less than a certain small x is the yellow region. And how do we calculate this? If you remember from your calculus or your previous math classes, the area under the curve is just the integral. In our case, it starts from 0 and it ends at small x, that is the yellow x, and we're integrating our f of x to get this specific region. And this specific region is going to give us this probability of large x being smaller than this x. Now, if we think about it, what if we take all of what we said, and instead of doing this every time, integrating, thinking about it a little more, and we can just represent this integral in a function. So if this function is representing the integral of this, so basically I can just go into any point over here and get the probability of my random variable value being less than this small x. So this function, let's go back one slide. This function is the integral of this function. So at any point, it's giving me the integral of 0 to x of f of x. So for example, if my x is here, it's giving me the integral from 0 to this point of this function. And this is basically my cumulative distribution function. It's summing the distribution until its end. And in the end, it will always reach 1. Because if you remember, when I integrate the full scale or the full range of my data, it will integrate to 1 because it's a normalized probability distribution. So this function will always end at 1 and it will continue as 1 from there because the probability of getting a value that is less than the max value is always 100%. So if I have data that is ranging until from 0 to 50, what is the probability of drawing a number less than 51? It's 100% because every data point in my sample is less than 51. So this is my probability mass, my cumulative distribution function, and it's represented as capital P or capital F. So basically P of x for a continuous distribution function is representing the area under the curve for the probability density function. So now what is it telling me? As we just said, it's telling me the probability of x smaller than or equal to this x, and it's equal to P of x, this function. And why is this useful? Because if you remember from a couple of slides ago, we said we're interested in the size of that slice. So what is the size of the slice going to be this time? If the slice is between a value A and a value B, let's say A is 3.5 and B is 3.6, and I'm interested in understanding what is the probability of my random selection falling between 3.5 and 3.6, it's just going to be the large P of 3.6 minus the large P of 3.5. Because they're going to take the difference between that large region and this little smaller region, and I'm going to end up with that shade of yellow in that specific range I'm interested in. So now we were able to conclude that basically the probability of x equals to small x is the probability of x being between a very small increment above and a very small increment below. And given my data is normalized, it's going to be just the width of that slice. Now, what are the features of a cumulative distribution function? Well, if you think about it, we said it will always end at 1 and it will continue like this. So if we take the probability of, not the probability, the CDF of infinity, it's always going to be 1. Because what is the probability of drawing a number that is smaller than infinity? It's 100%. Every number that we know is smaller than infinity. So it's going to be 100. If you think about the other side, What is the probability of drawing a number that is smaller than negative infinity? Well, negative infinity is the smallest number that we know of, so it's going to be 0. There's no way I'm going to draw a number that is smaller than negative infinity. It's strictly increasing because you're always adding probability, even though our original probability density dropped, but it was the area under the curve was still being added to the original area, even though its rate is now slower. So for example, if you see from this graph, it was the area was increasing in a very high rate, and then it started slowing down, but still it's always strictly increasing. It's always continuous to the right. So if I take the value, there's no sharp turns or no like two values for the same number, because it's a representation of an integral of a smooth function. So there's no sharp turn. So always the value that is just right to the value I'm interested in is equal. So for example, the limit of p of x plus a very small value that is almost 0 is the same as p of x. So as you see here, there is no sharp jumps in it. By sharp jumps, we're saying two values that are represented on the same line. So every number of small x has one value for p of x. It contains all the probability information we need about x. Because remember, anything that we want to understand what is the probability of x being smaller than a number. We want to understand what is the probability of x being between a certain number and a certain number. We want to know what is the probability of x being almost exactly that number with a small increment above or below. All this information can be acquired from the CDF. So we say it's comprehensive of all the probability information that we need. So very frequently you will start with your CDF and then decide if you need to differentiate it to get your PDF or you're satisfied with it. Now let's think about the last point of this video, which is how to move between the cumulative distribution function and the PMF or PDF and vice versa. So if we talk about the discrete random data, so for discrete we said we have a probability mass function. So to get the CDF, we just sum the probabilities until we reach 1, which means it's the full probability. So for example, if my proportion of data has 10% that are zeros, I will just say that I have 10% from 0 to 1. So what is the CDF definition? It's the probability of drawing a number that is less than 1. So what is the probability of drawing a number that is less than 1? It's 0.1. Or it's basically the number of zeros I have in my sample over the total number, which is 0.1. And now, what is the probability that I draw a number that is less than 2? Less than 2, strictly less, not less or equal. So less than 2 is basically either the ones or the zeros. So basically it's a 0.3. So as you see here, it's a 0.3. The same thing for the probability of drawing a number that is less than 3. It's basically 0.1 plus 0.2 plus 0.4 until basically we reach 1, because when we sum all of these values it's 1. So what is the probability of drawing a number that is less than 100? It's 1. What is the probability of drawing a number that is less than 5? It's 1, because all my numbers are either 0, 1, 2, 3 or 4. So how did we move from this small p of x to the big P of x? Basically we summed. So to move from the PMF to the CDF, you sum the PMF and you get the representation of the CDF. Now for continuous, it's a little different as we showed. So if my probability density function is like this, my CDF is gonna be the integration of this. So first we will integrate from 0 to, for example, 1, and we will get a function. Then we will integrate until we get to the point where the integral has one area that we reached it, and if you remember we said it integrates to 1. So the integral will eventually reach 1 and continue from there. So again, what is the probability of getting a number that is less than 5? It's 1, because all my numbers in my sample are less than 5, and so on. I can see that there is a mode of 2 here, or an expected value of 2, and it's represented with the highest frequency, but of course it's not 2 exactly because this is continuous data. So we can see that there is like a large increase until we reach 2, then the increase slows down until we plateau at 1. So basically, to get the large f of x out of the small f of x, we integrate the PDF, and to get the small f of x from the big f of x, we differentiate, because this is just representing the slope of this function. So we, at the maximum point, we reach a slope of almost 0, which is this one. Then our slope goes down the other way. And this, in a nutshell, is cumulative distribution function, probability density function, and probability mass function. They are the basis of understanding any inference we make about probabilities. In the next video, we're going to talk about something that is very interesting. We're going to talk about real-life example. So for example, if our data represents count data, how can we model it using common known distributions? If our data represents waiting times, how do we model it? If our data represents a natural phenomenon, what are the common distribution used for it? And as we remember from that slide a little while ago, the distributions, having a common distribution, allows us to understand the phenomena and make inference that is much more powerful than just making inference about the numbers that we have in our sample. With this, we end the video. Thank you for watching. If you like it, please subscribe and like the video and wait for the next episode. Good luck with your data analysis.